Before we start, any questions so far?
No, sir.
My screen is visible?
Yes, sir.
Okay. So, I hope
Sir, I have a question.
yes, please go ahead.
Sir, in the equation number 1, where we wrote du internal upon dt equals to minus delta W into enthalpy plus heat. So why we put minus sign with the first term?
Give me a minute. Okay, so now what is the question here?
In the equation number 1.
Uh-huh.
So why
So
is there
that
the
you
first minus sign?
that you should tell me an answer. Why it is, you tell me. I hope you have learned thermodynamics. You know, huh? Tell me why it is. Am I audible?
Oh, yes, sir, you're audible. Sir, even I didn't understand where this equation came from.
So have you? So I hope you have learned a course on thermodynamics, right?
Yes, sir,
So
we learned
delta
that.
WH means output minus inlet.
So can someone explain in the class based on your previous what you call experience how equation 1 comes? Huh? Hello.
So delta WH means flow of enthalpy out minus flow of enthalpy in. So
Okay.
if enthalpy is accumulating in the system, this means that inlet is more than outlet. So this will be a negative term. So we multiply by minus, so make it positive.
Okay. Then what about the second term?
So that's Q. Means delta WH means work done actually. Change in enthalpy is equivalent to work done, and we add it with the heat. This is equivalent. This is just first law of thermodynamics.
Okay. So is this clear now to everyone?
Yes, sir.
Yes, sir.
Thanks. So see, this is basic, just thermodynamics. You have to only look at the convention of how an enthalpy balance. How do you do it? You got it?
Yes, sir.
So this is pretty straightforward. So only thing we will have to look at the sign of the how the internal energy flow is happening. So is there any more confusion on this? So shall we go ahead? Hello.
Yes, sir, we can go ahead.
Yes, sir.
Okay, so let me scroll down. So we were at this point. So is equation 3, 4 is all clear to you?
Yes, sir.
Huh? Okay. Okay, so what are we going to do? We are trying just writing a heat balance. Okay, so the heat balance says the inlet, what do you call, the inlet heat input minus what do you call, so there is a, so there are two things, right? So one is heat that is supplied as an enthalpy, one is heat that is supplied separately via what we call either steam or heat. So now what are we going to do? I hope my screen is visible. Any confusion at the moment? Hello? Hello?
Yes, sir.
Okay, so I'm continuing. So equation 3 is basically the unsteady state equation, and if you assume that heat is mostly done, what I would say, heat is supplied via, let's say you can supply heat maybe by heating a coil, or maybe supplying what I would say, let's say by supplying steam. So let's say we are assuming that we are supplying it via steam. So that is what this means. So this would be the final equation eventually, and say as you would really see here, this is a dynamic equation and not definitely not in steady state. So what we could do is so we could figure out what is the steady state equivalent of this. The steady state equivalent of this could be found out by equating the left hand side to be 0, because there is no variability with respect to time. Okay, so then there is T bar. Fine. Then what I would say, so assuming that this is the nominal heat flow and W bar as being the nominal steam flow, okay, and of course the left hand side to be 0. So the equation 5 is derived from equation 4 by considering the steady state condition. I hope this is also clear to you. Any questions here? Okay, I'm moving ahead. So now what are we going to do is we will just subtract equation 5 from equation 4. So we need to have the equation kind of satisfied for both steady state and dynamic condition. So we are making this to what I would say, we are trying to make this applicable for both steady state and dynamic conditions. So we are just subtracting equation 4 from 5. That would eventually leave what? So left hand side there won't be any change because 0 is 0. So when we do a subtraction of the term 1, so Ti would cancel out. It would be T minus, in fact it would be T bar minus T. Similarly, it would be W bar S minus Ws. Okay, so now, so you could see that, so this is the final equation that is kind of applicable for both static and dynamic condition. Okay, so then let's say we are so just to make our temperature time isolated, we are dividing the whole thing by Wc. Okay, so that would eventually happen. The C would cancel out here. So rho V by W. So this would be standalone. It would be delta H by Wc. So now you see this is now you see that now these terms here are what we call as in deviation variables. So deviation variables talks about delta change. So because now everything is, so this is a differential equation. So dt stands for what? Delta change in temperature. Similarly, T minus T bar would stand for delta change in temperature. So we can suitably rewrite, okay, V rho by dt is equal to, let's assume that the whole, these are all constants because V rho and W are all constants. I will call them as tau, okay, and this is also a constant. Delta H by Wc, this is also a constant. Okay, this is, I'll call it as Kp because delta H, W and C are generally you will obtain from the tables. Okay, so then what are things remaining? So there is a T minus T, okay, and W minus ws. Okay, so now let me just write the left hand side term slightly generally. So so what I am going to do is dt by dt. I can also write dt minus t bar by dt. Will you agree on this? Anybody has a question? Hello?
It's clear, sir.
Because dt bar is a constant anyway. When you take the derivative, that derivative would be equal to 0. So t minus t bar, the derivative of t minus t bar and t is going to be the same because it's just a constant. So what I can now do is, it's now all the variables are now in terms of what is known as the deviation form. So let me now attribute a new variable y is equal to t minus t bar and u is equal to w bar s minus w. You will be able to kind of simplify the equation just like an ODE. Tau into dy by dt, where y is t minus t bar and u is equal to w bar s minus w. And this is what simply first order ODE, and you will be able to take, and this is also what is known as the separated variable separable form. So you will be able to write dy by y is equal to okay, 1 by tau into kp times u, and you can integrate both the sides. So this would eventually give you, of course, you will have to assume what is the value of u. Assume that u changes only by unity, you will get it an exponential profile out. So are we clear up to this? Any doubt here? This is very simple, so I am not telling anything new at the moment. Any questions so far? Is this clear to you?
Yes, sir.
So,
Okay.
hello, sir.
Go ahead.
So, what's the significance of coupling together the unsteady and the steady state equations?
Good question. So see, eventually you really need to have a dynamics that both satisfy both steady state and unsteady state, right? So eventually you can have, so well, let's say look at you are working on a process system. So sometimes it might operate in steady state condition, sometimes it might operate in unsteady state condition. Correct? Hello.
Yes, sir.
And so it would be important that your model captures both. Got it?
Yes, sir. Yes, sir.
And you see, there is no harm. So we have not done anything harmful here, because here the left hand side is a quantity x, correct? Fine.
Yes, sir.
Here the left hand side is 0. So even if you minus something by 0, the net output is going to be this. Correct?
Yes, sir.
So even we do the subtraction, we have not made anything, what I would say, we did not make anything we did not make anything incorrect. It's just a subtraction that yielded 0, that's all. Is that clear?
Yes, sir.
So yeah, so what eventually we've got a nice ODE that satisfies everything. So when you solve, you are not going to get t, but you will t minus t bar. To get t, what you have to do? You will have to subtract, add t to the solution. So y is t minus t bar. So when you solve it, you will get t minus t bar only. If you need to get t, you just need to add that bias, what I call as the steady state value to the system. Is that okay to all of you? Okay, so now let's try to see how the system response looks like. Okay, so eventually these kind of systems, we will talk about this slightly in detail. You would have a exponential, negative exponential dynamics. This is basically called as negative exponential dynamics. Okay, because this is a particular characteristic of first order system, because your ODE is first order, and we'll see. And there is, and we will come to know that there is some significance on this value tau, because that kind of characterizes the output. Okay, so now what I am trying to say is this is, so we really need this kind of models. So so when we are really going to do a process control, we really need these kind of models to do our job. So if you either what I would say, just a second, either equation 5, which is a steady state, or equation 4, which is only dynamics, might not work. We need to have a coupled, what I would say, equation that kind of characterizes both steady state and dynamic conditions. So I'll tell you why. So this is a typical example. So these are all, up till here, this is all dynamic, you see. So this regime, let me mark it black. Got it? Fine. So once it reaches a saturation, it has become a flat line. Correct? So in this part, your equation 4 would take prominence. In this part, your equation 5 takes prominence. So eventually, if you need to have both things in hand to characterize this, is this clear to all of you? So if you have only equation 5 in hand, you will only be representing this part of the process. If you have only equation 4, you will only representing this part of the process. So we need to have both. So that's the long and short. I hope this is clear. Any questions on this? Okay, so now, so the next is, let's say, so this is the model development. So you have developed the model, but eventually this is a, you see that this is a simple system. This okay. So first order ODE and all things looks okay. So the point is that so the point is that the first order dynamics is a simple thing to work out. Let's say your system is so complex. Let's say there is 2 heaters. Instead of one heating system, there are 2 heating systems. One is here, and you take an output and pass it over here. So it is a complex system. So what eventually would happen is things become complex and complex, and you will have very difficulty in deriving equation of the form 8, because this seems to be very simple, while the others are not. Okay, so now, so we'll stop this discussion over here, but we'll come back to this. So when we deal with more onto the modeling. So this is just a glimpse, okay? So once we have the model, what we really need to know the degree of freedom. So why do we need the degree of freedom? So the degree of freedom is essentially means what? Let's say we have any number of equation, nv number of process variable. Okay, the degree of freedom is basically their difference between both. So what does that mean? Okay. So NF is the kind of variables that you can play around, because for if there are equal number of equations and equal number of unknown, you have only unique solution. There is nothing to change, because the solution is unique. You got it? While if you have degree of freedom, so these degree of freedom are our, what I would say, is what we could play around to figure out or manipulate to achieve the desired control. So if there are no degree of freedom, then it does mean that you cannot control the system, because the system has a fixed dynamics. You cannot vary anything. But if most of the system will have excess degrees of freedom, so you will have to identify which of these are input variable which are manipulated or disturbance. So most of the time when we calculate this NF, which is the degree of freedom, this degree of freedom could be either, so some of them would be, of course, you don't have any control, they would eventually directly become the disturbance variable. Some of the you may have control, they will become the manipulated variable. So basically what I'm trying to say, each also the degree of freedom you might have learned in a very different context, in maybe in phase rule and maybe in thermodynamics and things like that. So here also it has a meaning, but slightly different meaning. These are the number of things that you could specify or vary so that you can achieve your desired control objective. So for in this case, so we will take about that. Okay. So let's look at this equation. Just a second. Yeah. So I am going to erase this. So once you have this equation 7, so equation 7 and 8 is technically the same, only thing that we have simplified it, okay? So equation, so let's say we have reached up to a stage of equation 7. So the next thing is identify and enlist what are your parameters, okay? Okay, total variables, the relations that connects parameters to variables, okay? Then what is the degree of freedom? So if you reach 7, so we'll be able to identify this. So let's count how many variables do we have. First of all, how many parameters do we have? So can someone say how many parameters are this in question 7? Can someone say how many parameters there are in equation 7? So what are parameters? Only 2? So tell me, what are those?
Temperature and time.
No, so they are not parameters. So what are parameters? Parameters are the things that are fully independent of your dynamics. So there is no somebody. So parameters are the one that would be fixed externally. You don't have any control on this. I'll tell. One is heat capacity. You don't have any control. If you fix a fluid, your heat capacity is fixed. Correct? Density. If you fix your fluid, the density is fixed. V. When you fix a vessel, your volume, so when you decide the size of the vessel, volume is fixed. Got it? So I'll say there are 3 parameters. Okay, so how many relationship equations do we have? Sorry, yeah, we are at equation 7. How many relationship do we have? We have only one equation that connects all the variables. And how many variables? How many variables in the sense that would vary with respect to time? How many variables do you have in the overall process? Can someone say? Hello.
4.
Agree. So, what is the degree of freedom? We'll come to the last slide here. Okay. So the degree of freedom we have 4 minus 1, which is 6. So we can look at this equation and figure out what all things we can vary. So overall, so you have 4 degree of freedom, you can say. So 4 variables you can independently vary in this equation. So be it what I would say. So you can look at, right. So one is steam flow, fine. Okay, inlet temperature, fine. What I would say, outlet temperature. Okay, so W, so I should not say Q, so we will have W bar also. So technically this is not TI T bar. So that is what we have kept, right? Yeah. So TI T bar, W bar is W. So these are the 4 variables that you can play around with. And okay, so consider this as a typo. So these are the 4 variables we can play around with. And you have one equation that, and which means that you have 3 degrees of freedom. So which means that you can vary at least 3 things to make things controlled. So let's say if you got it either negative value of this, which is quite unlikely, or 0, which means that your system parameters are fully specified, you have very limited way to kind of play around with them.
Hello.
So,
Hello.
so
Yeah.
any question? There are no questions. The
Steam
question
again.
is
कर ले. फोन से कर ले.
hello.
Samarth, your mic is unmuted.
Please.
के. और तुम्हारी एक बाद में कर.
I muted it. So first thing, so see, first thing when you are given an assignment for designing a controller, this is what we do. First of all, what we do, model development, okay, including static, dynamic, okay, then degree of freedom, fine. Then identify. So then that would give you an idea what are the variables you could play with, okay. So eventually when you classify, you should be able to either fix one of these, okay. So your variables could be either manipulated. Control variable is anyway pre-specified because that is what is given as your objective in the starting, fine. So the degree of freedom you would be either translate to either manipulated variable. If variables that you can directly control, then they are all become the manipulated variable. There are no control in certain variable. For instance, inlet temperature for that heater, because if it is coming from some downstream process and you don't have any control, then TA cannot be manipulated. It can be a disturbance. Okay, but okay, so let's say you have a means to control TA, then it become manipulated. So it depends upon the overall characteristics, you will figure out what is manipulated and what is disturbance. Control variables are already prefixed, so you have very limited hand on that. Okay, so now coming to the in this process, okay, so the variable would be classified as, of course, output variable is T because this is what you need to control. Control objective because you need to control the temperature. So number of degree of freedom, you may call them as a placeholder name called input variables or number of degree of freedom, that's okay. One could be the inlet temperature, one could be W from here, fine. And other is Q, which in what way you want to add Q into the system. So either you may write as still Q, or you can say either in terms of WS or W bar S. So you can play around, or you can increase or okay. So now depending upon what is the condition, as I told, if there are no control on the inlet temperature, then it becomes a disturbance variable. If there are no control on W, it becomes a disturbance variable. Let's say if you can control the heat, which is W H bar S from here. So let's say this is how you are going to. If you have a control on WS, this becomes a manipulated variable. While W, you may not have any control, because you see, this is a system with a. If there is no control valve here, you may not be able to control. So again, as I told, I may not be, I can, instead of this Q, I would like to write as WS, because Q is not there in that equation. So Q is essentially controlled by W. So I would like to call it as the manipulated variable WS. Okay, so now in the system that you are working with, if there is a means to control these, they can be lumped into manipulated variables. But let's say if none of this could be controlled, if you have no means to control any of this, okay, then all would become disturbance variable. Is this clear?
Yes, sir.
Any questions so far?
So in the slide above, I think they've written the input variable as NF. It should be NV. Sir, above this. Yes, at the last point.
No, that is correct, no, because the input variables. So see, NV is the total number of variables, NE is the number of equations, and remaining is what you can play with. Okay, so I will like to call them as they are all input variable to the system, because they are all acting into the system. Out of this NF, few could be manipulated, few could be, you cannot have any control, they could be disturbances. Is that clear? So NF, number of degrees of freedom, is equal to total number of variables minus number of equations. Is this clear? So,
Yes.
so who was asking that question? Sruta.
Yes, sir. Yes,
So-
it's clear now.
So this NF could be either lump, because they are all acting into the system. So they are technically inputs to the system, because they are acting onto the system, they are input. But now you could classify them as either manipulated or disturbances based on its characteristics. If you don't have any control on this variable, then you would put them in the bin of disturbance variable. If you have some means to control over them, you would put them in the manipulated variable, which is that you would use for control. So if you are given an assignment of designing a control system to any process, first thing that you would identify is do this analysis and come up with your number of degrees of freedom and classifying them as manipulated variable or disturbance variable. So that would give you an idea what is the instrumentation that you need to put in to achieve all of this. Is this clear?
Yes.
Any questions on this? Okay, so if that is the case again, so we shall move ahead further. Okay, so now we are actually changing gears. Okay, so this is something that you have never learned as part of any prerequisite. Here is how real process control gear shifting starts. So what all things we have learned till now? Okay, so if you need to have so our objective is controlling something. Okay, for controlling we need dynamics. Okay, and so in fact I would like to call it as a model that sufficiently capture both steady state and dynamics. Okay, okay, from if you have that model available, okay, then you will do a degree of freedom analysis and figure out what is your manipulated variable and what is your disturbance variable. We have learned till that time. Now now we are trying to see a bit more into the dynamics and see what is that we are what all dynamics is of key interest to us, and how are you going to control those dynamics. So now what is the problem? So what was the first observation that we found? When you develop a dynamical model, they are either into ODEs, falling into ODEs or PDEs. Agreed? That's what we have seen. The equation 7, what we have seen was a ODE. Is that agreed?
Yes.
So, if you need to know the dynamics of that, okay, ODE will not give you any dynamic. You need to solve the ODE. How do you solve an ODE? That requires an analytical or numerical integration. And this would eventually bring in lot of computational burden. Sometimes if it is an analytical, it's going to be heavy. Numerical, there is issues with convergence, step size. I hope you are learning or have learned a course on numerical methods. Have you learned? Or you are learning now?
We have done.
So you see that you have seen about the convergence, step size and stiffness, so many issues. So now what is the problem now? So if you and what you really need a decision making in seconds to minutes. And you are not just looking at a reactor and a heating. You may have the whole plant that contain multiple components. So it may be a ODE of so not so whatever we have seen is just a ODE of degree 1. It could be a higher what you call higher order ODE. Okay, it may be very difficult to do that. So let's assume that we are all working in the linear domain. So forget about the non-linearity for now. Assuming that everything is linear, even though, see, the funniest aspect is that even though your ODE is linear, the dynamics is non-linear. Are you getting what I am trying to say? Give me a minute. So the ODE that we have seen was a linear ODE, tau into dy by dt, so on and so forth. So, but even though that's a linear ODE, its solution is non-linear. Are you getting that point? So you have to understand that. Tau into dy by dt plus k times y, I think plus y plus k times u, or that is k times u. This was the ODE that we have seen. Or I think no, it's like this. Tau into dy by dt is equal to. So let's clearly check what we have seen. So our ODE was seemingly simple. tau into dy by dt is equal to minus 5 plus kp times linear ODE. But you see that your solution has become nicely non-linear. There's an exponential term comes in. So even if you are working in the linear ODE domain, the solution can be non-linear. That is something that I wanted to tell you. So another point what I wanted to say is, let's say assume we have all non-linear ODEs. If it is linear ODEs, if it become non-linear, things become more complex. But still, your solution has become non-linear. You will have to deal with all the step size and things like that, lot of issues. So somebody has found that if you apply Laplace transform of the ODE will become simple. The ordinary differential equation become corresponding algebraic equations. So what is the advantage? So when you apply Laplace transform to a system, corresponding ordinary differential equation become algebraic equation. So what you could do, all your analysis become faster because it's like a. So have you learned about Laplace transform before in your MTL courses anytime?
Yes, sir, we have.
Hello.
Yes, sir, we have.
Okay, so so what is that we are trying to say? So Laplace transform. So first of all, let's understand what is Laplace. It's just a transformation. So let's say, I'll say this is time domain. And you do some transformation to Laplace domain. And of course, you will be able to convert back. All the Laplace transformation you can convert back into time domain also. How do you calculate the Laplace transform? L of f of t is an integral of 0 to infinity f of t minus st. F of s is the Laplace transform function. Okay, and s, of course, s something you understand. S is a complex variable. S has an I component, so S will have a plus j omega kind of a form. But anyway, we'll see that. So L is the Laplace transform operator. So what is the advantage of Laplace transform? Laplace transform, if you convert any ordinary differential equation into Laplace domain, they become algebraic. It's a magic. You see, things are ODE here. In the Laplace domain, they become algebraic equations. So what is the advantage? Your complexity in dealing with the ODE becomes simpler when you are in the algebraic space. Got it? And there are some other advantages. Many. So there are many other advantages. So see, so one of course is if you have two time variables and when you take the Laplace transform, it would be additive in nature. So let's say this is an ODE, this is again an ODE, y of t. Eventually this becomes the summation of two algebraic equations. And you also have a very clear path of, so it's a unique transformation, time domain to Laplace and Laplace to time domain. So which means that if you convert x to x of s, and if you do an inverse transform, which is L inverse, you will get exactly x back. There is no information being lost. So somebody who is working in this area much earlier have observed this thing. So anyway, when you need to do control, you have to deal with complex ODEs and PDEs, which is difficult to deal with considering this aspect. Okay, so let's not do the let's not do the analysis in the ODE space, even though they are representing the dynamics because of its complexity. Let's move ahead to a regime where you have much more freedom to play around. So once you have the ODEs, you don't do any further analysis. Okay, you will convert them into the Laplace domain, so things become algebraic, and whatever you could do, it much more easier to figure out. Are you getting this message?
Yes, sir.
Any doubt on this?
Sir, we do have some numerical method to solve non-linear equations as well. Then why do we need to convert them to algebraic form?
Okay. See, there is no harm in using. So we are acknowledging the fact that you can do numerical methods to play around with. But only problem with the numerical methods, of course, I hope you would also see, it is iterative in nature. Correct? You might have heard RK, Runge-Kutta, celebrated
Yes, sir.
ODE solver. Runge-Kutta is an iterative approach. It is also depend upon your step size h or whatever you call. In fact, there are 4 h's. It is most of often you will have 4th order Runge-Kutta, na? And you have finite difference. All of them are iterative in nature, and it's also strongly depending upon step size. So let's say, so I'll tell you. So let's say, what do you mean by step size? So you wanted to solve between t to t plus 1 ordinary. So let's say you want to solve the problem between t to t plus 1. You would break the overall time space into 2, and each of the small time space, you assume that they are discrete in nature. Correct? That's what step size means.
Yes, sir.
And you would solve for the small step size, and it would be an algebraic equation. Then from here, from here, from here, from here, from here, from here, from here. So you solve it basically by making small algebraic equations. So for instance, what are you doing here? dy by dt, you discretize. How do you do it? Yt minus 1 by delta t. Correct? And this delta t is as small as possible. And you slowly integrate until you reach your t plus 1. Okay, so between two time spans, let's say your time is 5 seconds to 6 seconds, and your equation is highly stiff, you may still need to take 10 steps, 15 steps, so on and so forth, or maybe more than that. Most of the solvers that you have using is adaptive step. It would check for the step size on its own. Okay. So the only problem that you would encounter is this is highly tedious. And if you could get things without doing that, it is faster, no? I hope you understood the message.
Yes, sir. I got that.
So basically, if you need to take a decision in 1 second, your solver is taking more than 5 seconds. Then there is of no use in doing a finite difference approach. Agree?
Yes, sir.
Okay. So now, so let's say what I am trying to say is, so some of them I will not go into the detail. So it's a review. So please review Laplace transform. So now here onwards, take a review of the Laplace transform which you have learned. I also put something in the notes. Okay. And you have this Laplace transform table available in the book, in down wherever. So which means that somebody has done all this calculation for you. For instance, for unit impulse Laplace transform is 1. For a step, what do you mean by step? This is step. For a step function, Laplace transform is 1 by s. For a ramp function, what is ramp function? Varying with respect to time. T, it is 1 by s square. But how are you getting this? You are just doing the integration. So how do you calculate the Laplace transform of a constant? Let's a be the constant. Integral of minus a into s, e raised to minus st dt. Okay, so you take the a out, integral of minus st by 1 by s into minus st. Of course, this is a definite integral. You substitute 0 to infinity, it will be a by s. So you will be able to calculate this for many standard function that you would need. It could be a step function, it could be exponential functions, as you would really see, to sine function, cosine function, so on and so forth. There are many standard options available. And somebody has very nicely done it for you. You only need to use them. It's like logarithm table, right? Logarithm table is give you a console. You don't have to calculate the logarithm. You only have to use the table. Similarly, this has been done for many functions, especially, so we have to have a very careful look at the derivative function, which is L of f df by dt. It would be s times f of s minus f of 0. F of 0 is the function value at the 0. If f of 0 is equal to 0, this term would go 0. Okay, then many such examples. So I would request you to take a what I would say review of Laplace transform, or all basics, whatever MTL you have learned, or maybe in the textbook some contents, and come back to us. And now we will use this Laplace transform, whichever is there in the table, book, wherever. Directly use them to convert, I would say, all this differential equation into nicely Laplace domain. So I'll tell you, see, this was our ODE, you see, equation 14. There, it will nicely become two addition terms. Got it? When we do various analysis, we'll come to that. What I am trying to say, this is what is the outcome. It is much more simpler to handle compared to a complex ODE. So this gain, so we are trying to leverage this gain by converting this ODE thing into corresponding algebraic equation. So which will be easier to deal with. So I will stop here, and so there are 2-3 things of important. What is final value theorem and initial value theorem? You can again read. So you can calculate y infinity by substituting s is equal to 0 into sy of s. Initial value theorem, you can calculate y is equal to 0. What is y infinity? Y at t is equal to infinity. Yeah? Y at t is equal to 0. So you don't have to plug in. So see, otherwise, how do you get this y of infinity? You have the ODE, okay? You have to do any, you have to either solve it using explicitly or numerically, then substitute t is equal to infinity. So now what you have to do, you have to just take the Laplace transform and substitute s is equal to 0. Very simple, you see. You're not worried about doing all the steps. It's become very fast here. Similarly, the other way around, initial value theorem. Okay, and so two other things as of interest is integral f of t, the Laplace transform would be 1 by times f of s, and something known as translational theorem, which is little, if something is translated by a factor theta, the Laplace transform would be the transform of the original variable times e raised to minus s of theta. Again, very nice decoupling. So all of this would be available in any standard Laplace tables. So we will use them as a tool. We will use the table and calculate. Or sometimes some complex function like this, we may even derive the Laplace transform, assuming the first principles. What is the first principle of Laplace transform? Laplace transform of a function f of t is equal to integral 0 to infinity f of t raised to minus t dt. That's all. So I'm going to stop here. There is no class on Saturday. I generally do not take class on weekends until and unless it is we are in a tight schedule. I think we are okay as of now. We will see if things are getting dragged towards then we can schedule something. But at the moment, it's okay. So no class on Saturday, and we'll continue from next Tuesday. Okay.
Sure, sir. Thank you. Thank you, sir.
Okay. Bye bye. If you have
Thank
any
you, sir.